directives, you have written the what C language codes. Okay, so which are the preprocessor directives? You have discussed it in the C language. In C language, you have used preprocessor directives like hash include, hash define. That hash indicates that is a preprocessor directives. Okay, so here also in Verilog we have some pre what compiler directives. Those preprocessor directives here we have called it as compiler directives. Okay, so there are two compiler directives we are discussing in Verilog language. Okay, so how that compiler directive we will write it in Verilog language. What is the standard syntax? Okay, so here I think in your slide you can see. So compiler directives are defined in Verilog by using the syntax. This one should be a standard syntax for writing the what compiler directives in Verilog language. How we are writing in C we are indicate by using hash symbol, but here in Verilog language, so we are indicating that compiler directives by using tick mark. Remember it. Any keyword should begin with a tick mark, then that should be, we have called it as compiler directives. Okay, so this one should be a standard syntax for writing the compiler directives in Verilog language. Okay, tick mark keyword, write it. So here keyword is what? Include, tick mark include, tick mark define. These two are the what compiler directives we are using in Verilog language. Okay, so there are two most useful compiler directives. They are tick mark define and tick mark include. Okay, in C language also we have studied same what preprocessor directives. That should be we have indicated hash include and hash define. Okay, function should be same, but syntax should be little bit changed. Okay, here compiler directive should begin with tick mark, but in C language, so that preprocessor directives are begin with what hash symbols. Okay, so what is the function of tick mark define and what is the function of tick mark include? We will discuss. Okay, so here, so first we will start tick mark define. Tick mark define. Tick mark define. So the tick mark define directive is used to define text macros in Verilog. Okay, so here we have some text macros. So that text macros, if you want to define in your Verilog code, so at that time we are using tick mark define. Okay, so I will give one example. So here, but software don't know some what words, some syntaxes. So before that, we need to define it. Those we should define before the program. So after that, we should start for writing the codes. So at that time, we will use tick mark define. Okay, so that how that we are using in what Verilog language, how we will write it, in which format we will write it, that tick mark define. We have written tick mark define, that is a keyword. So next macro underscore name we should write it, that is followed by that macro name. Okay, so tick mark define is similar to the define in C programming language. Remember it. Okay, so I have given some one or two example in your slide. You can see. So first example I have given. So I have written comment. So after that comment, we have written a standard instruction syntax. Okay, so define a text macro that defines default world size. Okay, so here we are using one text macros. That text macros defines the default word size. Okay, so we are using some word, that word size we require it in your program. So that we should define it. Okay, so that used as that variable should be written in this format, word underscore size in the code. Okay, so how will you define that? Is tick mark define word underscore size 32. So this one we are defining is nothing but word size is equals to 32 we are using in your code. Wherever we require this what definition, you can use it directly word underscore size. Wherever we have written word underscore size, so at that time automatically that software will take it 32. Size should be 32, it will take it. Okay, so such things we should use it in your programs. Next, we'll move to the second example. Define an alias. A dollar stop will be substituted wherever yes appears. Check it here. In your program, what he is telling, so wherever yes should be appears, so at the time we should stop your execution. We should stop the execution of your program. So that we should mention it. So how will you write the what that using tick mark define? So at that time we should write tick mark define yes dollar stop. We are defining yes. So wherever yes should be appears in your program, we should stop the execution of your program. Dollar stop is nothing but will get current simulation time. Okay, so that is a instruction we are using for wherever yes should be appears in your program. At that time, your program execution should be stopped. Okay, next, define frequently used text string. How we will define it? So that should be defined by using this tick mark define word underscore register register 31 down to 0. We have what register set, that register set should be a 32 bit. How will you define it? By using what tick mark define. So we will use this one. Any new variables are there, directly that new variables we have used in your program, so at that time we should define it by using tick mark define. Okay, so next we will move to the next compiler directives, that is tick mark include. I think tick mark include is similar like hash include. So hash include you have written in your C language. Okay, so here the tick mark include directive allows the include entire contents of a Verilog source file in another Verilog file during compilation. Take there. So in your, I think C language, we are used hash include stdio.h. What it indicates? Okay, so whenever we are writing the your C language program, so we require some header files. With the help of header files, we are writing the programs. So because of that reason, so we have included some header files. Standard input output files we have included in your programs. Okay, so if you want to include such files, so at that time we are using tick mark include compiler directive in Verilog language. Okay, already we have one program. Within that program, we are including some other programs or some other header files. So at that time, we are using tick mark include. With the help of tick mark include, we are including the files in your program. Okay, so here tick mark include is similar to the hash include in the C programming language. Okay, already maximum students you have used hash include whenever we are writing the C programming language. Why we have written hash include in your C language? Same in Verilog language also you should use it. Instead of hash include, we should write it as a tick mark include. Okay, so this directive is typically used to include header file. Remember it. This why we are using this function. So Okay, so in this code, so I have written one example. You can see that using a tick mark include. So tick mark include header.v. So here, so we have some Verilog header files. We have some Verilog header files. So because of that reason, we have included those header files in your Verilog code. Okay, so at that time we are using tick mark include in your programs. Okay, so I think whenever we are writing C language code, so at the time also all C language code should begin with the hash include stdio.h. So because of that reason we require those what header files. With the help of header files, those header files we are using in your C language. Here also in verilog dot v is nothing but verilog dot v is nothing but verilog. So here for execution of Verilog code, we require some header files. Okay, so those header files, if you want to include in your code, so at that time we are including with the help of this compiler directives. Tick mark include, we are including some header files in your the program. So any new things if you want to include in your program, so at that time we will use this compiler directive. Okay, so this is about compiler directive. Next, we will move to the next concept. So that is what model and force. Okay. So okay. So am I audible?
Yes, sir.
Yes, sir.
Okay. So I think so whatever we have discussed up to that. So first model two, first half is completed. So these all we have studied theoretical part. Okay, so this second half is also a theoretical concept, but how programming we are writing, those all keywords we will discuss it. Okay, so in this second half, that should be we have called it as model and ports. Okay, so here in Verilog language, so all Verilog codes begin with a module as a predefined word. So what all of the parameters should be contained within that code? We will discuss all the parameters. Okay, so because of that reason, so we are called it as model. Next, for writing the codes, we are using ports. Port is nothing but port, input, output, in out. That should be, we will call it as some ports. It should be act like a input as well as output. So that port we'll call it as a in out. Okay, so about the port also we will discuss it. Okay, so because of that reason, in second model, second half should be related with model and ports. Okay, so if you want to write the codes, this concept, whatever concept we are discussing now, this one should be very useful. So in next class onwards, we will move to the model 3. So next class or otherwise next class onwards, we'll move to the what model 3. So in model 3, we will write only codes. We are not discussing any theoretical concept related to that neural modeling, data flow modeling, that theoretical concept we will discuss. We will write the codes. But how code should be written, general syntax, we will discuss now. So what are the keywords we are using? So that we will discuss it in the what second model, second half. Okay, so that should be, we'll call it as model and port. Okay, so carefully, so all should hear here. So what is model? Model is nothing but group of components. Group of components combined together. We have framed one model. That should be we have called it as model. Okay, so whenever we have framed one model, by using that model, we have to execute some operation. Then only we will call it as model. Otherwise, no. Okay, so before forming the model, we have some objective. We have some motto. That motto we should reach it. If you reach the motto, then whatever we have formed, that should be, we will call it as model. Otherwise, no. Okay, so here a model is nothing but group of what components or group of set of components should be collected together to get the what some operations. So that should be, we'll call it as model. Okay, so here in Verilog language, so all codes, all Verilog code should begin with module as a predefined word. That model we have called it as a keyword. So whenever we are writing the keyword, we should write it by using what lowercase letters. Remember it. So in your Verilog code, it should begin with module as a predefined word. Why all Verilog code should begin with model as a predefined word? You will get a question. So at that time, what you should do it? What is your answer? Why all Verilog code should begin with model as a predefined word? So here in Verilog language, we are writing the code for one model. Okay, so depends upon our motto, depends upon our objective, we have formed one model. For that model, so we are checking the operation. So whatever motto should be there on our mind, so that should be reached or not. We should check it by writing the programs. Okay, so because of that reason, all Verilog code should begin with the model as a predefined word. Okay, in your slide you can check it. So in your exam, will get one question. So compulsory in your exam, this question should be appear for 10 marks or 8 marks. Explain the components of Verilog model. These so whatever block diagram should be showing in your slide. So that should be a components of Verilog model. Okay, so first what you should do it, you should understand what question should be appeared in your exam. So here we should write the components of Verilog model. For writing the Verilog code, so which all are the components we require it. You should explain it with the help of block diagram. So within the block diagram, so what all are the components for writing the course? So what all are the components we require? So those should be we should call it as what components of Verilog model. So this component of Verilog model should be divided into three parts. No need to study it. So please give the more concentration. Okay. So here this whole block diagram, in block diagram you can check it. That block diagram should be divided into three parts. Okay. So I have drawn rows. I have drawn the one whole block. So how many blocks are there? You can check it. There are three blocks are there. Okay, so mainly that whole block diagram should be divided into three parts. So first part should be, we will call it as model definition. So what all are the, we are defining within the model. We are we are forming one model. So what all are the model definition? What we should write it in first part. We will explain it afterwards. Okay, model one is, so part one is model definition. First part we are showing there. So that should be, we will call it as what? Model definition. Next, second one we have called it as components of model. Those in the second block we have written there are five blocks are there. There are five blocks are there. Those all five blocks we have called it as components of model. Next, third part we have called it as end model statement. If all our motto is reached, then we should write the end model. Okay, by writing the end model, we will suggest to the software our program is completed. This one should be a third part. These are the three parts. If you return, so at that time our program is completed 100%. If these three parts should be there in your program, then 100% your program is completed. If any one part should be missing, at that time your program should not be executed. We cannot get the result. Okay, so I will explain one by one, there are three parts are there. So part one we have called it as model definition. For writing the codes, whenever we are writing the codes, these three parts should be very useful. In all Verilog code, these three parts are there present. Okay, so here in your slide you can see it. So there are three parts are there. So part one we have called it as model definition. So here in the model definition, so I think whenever we are writing the code, so we will write it for take an example of full ladder. So we will write it a model full ladder. So within the bracket we will write all the input and output ports. So after that we will differentiate it, which are the input and which are the output. These three syntax we will write it. These three syntax we have called it as model definition. Okay, so here which model we are constructing for that model. So what should be the name we have given? That is a model definition. So which are the input and output ports? That should be, we will call it as model definition. There are three syntaxes, we will call it as model definition. Okay, so I have explained that model definition. We have written some three sentences in the model definition. We will read it. A model definition always begins with the keyword model, remember. Right? So always your model definition should begin with a model as a keyword. So first your code should begin with model as a predefined word. That should be contained in the model definition. That is the first syntax. Next, go for next one. So next, after that, model should be followed by model underscore name. That is a second component. Okay, so that model underscore name is also contains in the model definition. Okay, so what all are the rules for writing the model underscore name? Already I explained it. Okay, so model underscore name should begin with alphabetical letter. It cannot be start with the number. It cannot be start with any special character, but it can include a special character like underscore. Okay, so those are the rules for writing the model underscore name. Okay, after that, port list, port declaration are present only if the model has any ports to interact with the external environment. Is nothing but whenever we are constructing a full ladder, for that particular full ladder, so which are the inputs and which are the outputs? Those should be connected to the external environment. A, B, C, in. So those we should write it. Which are the input and output ports? So those all should be contained in the model definition. Remember it. This much with first three. First three in all the programs we are writing first three syntax. Those should be, we'll call it as model definition. But within the model definition, we cannot write in the what operation of the circuit, operation of function of that particular circuit, function of that particular project, function of that particular model. We are not written. But what we have written? Only definition we have written. By seeing the definition, what we will get it. What we will get it or what so that software we will execute. So only it will take the what block. It cannot execute the operation. So what are the input and what are the output? It must that much it will show it. But we cannot get exactly full ladder output. Is it clear? Yes, we have written that next two parts. Next part, components of Verilog model. That components of Verilog model, within the components of Verilog model, operation should be what present. Operation of that particular circuit should be present in the components of Verilog. Okay, so there are 5 components within a model. They are. So whenever we are writing after completion of model definition, so next part should be, we have called it as what components of Verilog model. So within the components of model, so there are 5 components. There are 5 components. First one we have called it as variable declaration. Variable declaration is nothing but, so when we should go for variable declaration. So here in some program, what we are doing, some variables we have declared it. So with the help of variables, we have written the programs. But those variables we are not using in the model definition. Within the model definition, only main variables, main inputs, outputs we have written. But these some variables should be intermediate connections are there. In intermediate connections, we have given us some names. Those should be, we have called it as variables. So those variable, those should be present in your code. So those we should declare by using variable declaration. Okay, those should also we will write it in components of models. Okay, next data flow statement. We will write the data flow statements. Data flow statement is nothing but Boolean expression. So by writing the Boolean expression, we will get it. So that is the operation of circuit. Okay, so if you are writing data flow description, we will write it data flow statement. If you are writing behavioral statement, behavioral description, so we should write the behavioral statement. Next, task and functions. Next, any lower models are there. Those all should be contained in the components of model. Okay, these components can be in any order. Remember it, any order you can write it, no problem. First you can write behavioral blocks. Next you can write it data flow statement. Or first you can write it data flow statement. Next you can write it variable declaration. No problem. In any order you can write it. Your code should be executed. Okay, so I indicate any place in the model definition. Okay, so next, third part we should call it as ending model definition. Here model definition is over, components of model are over. Next, your program is 90% program is completed. So after completion of your program, we have to write the end model statement. If you return end model, then that software will get it. Yes, your program is completed. If you are not written end model, so at that time still that user will write some other statement. So because of that reason, software cannot execute your program. Okay, so because of that reason, after completion of your whole program, we should write compulsory end model statement. For writing the end model statement, we have some rules, we should follow it. Which are the rules? So first rule, so whenever we are writing end model, don't leave the space in between end model. Don't leave the space in between end model. Both we should write it connected, both connected, end model. Don't leave it. Okay, after that, don't give the semicolon to the end model. These two rules you should follow it whenever we are writing the end model set. Okay, okay, so this one should be a theoretical concept about what components of very log model. Components of very log model. This one should be a theoretical concept. Next, we'll give one example. I will write one program. Okay, so all of you see here. So all of you see the slides. Okay, so I will change the slide. So in that slide, I have explained one example. Okay, so so in this slide you can check it. So I have written one example for the about theoretical concept. Okay, so here in this slide you can check it. I am showing one diagram, one logical diagram. Can you identify it? Can you identify which diagram is it?
Yes, sir.
Yes, which one?
Yes, sir. Let's.
Yes, very good. That is SR latch. Okay, so here we are writing the program of SR latch. Okay, in your exam, he will give you title of the program. Otherwise, instead of title, he will give you directly logical diagram. That logical diagram you should execute with the help of program. You should write the program. So this logical diagram should be your output. You should show it in your software. How will write the program? Okay, so here, if you want to write the program, so we should remember that three parts of component of what components of very long model. So first part is model definition. We should write the what we should write the model within the model definition. First keyword is model. Next model underscore name. So which are the inputs outputs? This much should be contained in the model definition. Remember it. Okay, so here we have SR latch logical diagram. So that should be constructed by using two NAND gates. Okay, so for SR latch, we should have two inputs and two outputs. So two inputs I have called it as first output I have called it as S bar, and second output second input I have called it as R bar. Next, here we are getting two outputs. So first output we have called it as Q, and second output we have called it as Q bar. So depends upon this connection, we should write the code. How will you write it? So I have written. So after that logical diagram, you can check it. I have written the code. Okay. So here, how will write the program? So always all Verilog code should begin with model as a predefined word. I have given it model. So first I have written model. Next, SR underscore latch I have written. That is a model name. Which model we are constructing here? SR latch we are constructing. For writing the model underscore name, we have some protocols, we have some rules, we should follow it. By using those rules, we should write the that model underscore name. Okay, so these two should be contained in the model definition. Next, after writing these two sentence, next it should have input output. Within the parentheses, we have written inputs as well as the output. Okay, all four I have written. All four I have written. But what should be the next sentence? Whenever we have written all four variables, so which all are the inputs, which all are the outputs? We are getting that question. So because of that reason, in next sentence, we should write, we should differentiate it, which all are the input and which all are should be the output. Which all are acts like an input and which all are acts like a output, we should differentiate it. These are the three sentences. Syntax should be present within the model definition. Remember it. Okay. So by seeing the model definition, what we are getting? What we are getting for seeing the model definition, we are getting, we are constructing SR latch. For SR latch, so we are using four variables. So first two are the inputs and second two are the outputs. That much we are getting, but we cannot get the operation. Is it clear? Okay, so because of that reason, output I have written Q and Q bar are the output by using the keyword output. Next, after that input S bar and R bar. So in any order you can write it within the parenthesis, any order you can write it. No problem. First you can write it output, first you can write it input, no problem. Okay, so because of that reason only in next line we have differentiated it. Which are the two inputs and which are the two outputs. We have written by using keywords. That keywords itself will suggest these two are the inputs, these two are the outputs. Okay, so after that we should write the what next components of model operation. We require operation. So next two sentences are the operation. How many gates we have used here? Two NAND gates. So because of that reason, in your uh, program, we should write the two NAND keywords. Those are the operators. This one should be, we'll call it as a gate level description. This one should be gate level description, or otherwise we have called it as a structural description. Directive we have written. First, here there are two NAND gates we have used. So first NAND gate I have called it as N1. Second NAND gate I have called it as N2. That should be a block name. Okay, so two blocks we have used. So first block name I have given it as a N1. Second block name I have given it as a N2. Why we have given a block name? Without giving the block name also, your code is executed. But why we should provide the block name to the your code? So here, in some complex digital circuit, we have 10 to 15 NAND gates are there. 10 to 15 NAND gates are there. So at the time, I should identify it. This expression is for this gate only. Is it clear? So for that purpose, we should give the what names, block names. I will give you some example related to your names. Okay, some 5 to 10 akshata are there in your class. So at that time, how will you identify it? How will you identify it? We require at that time surname. Okay, so by whenever you have written surname, so at the time direct easily we will identify it. So because of that reason, here also all we have NAND gates. all 10 to 15 NAND gates are there. So because of that reason, block name should be compulsory. We should provide it. Without providing the block names, your code is executed, no problem. But for our identification purpose, this expression is for this block only. For that purpose, we should provide the block name. Okay. So how will you write it? So first we should write the NAND. Next block name for that expression is for N1. That we are writing the N1 block operation. By seeing that expression, we will get it. Yes, first block should be executed. Okay, NAND N1. So first compulsory within the bracket, we should write the what? Outputs. Outputs. But within the model definition, you can write it any, no problem. First, you can write it output or otherwise input. But here, whenever we are writing that port map expression, so compulsory we should write the output first. Okay, NAND N1. So which is the output for N1? Check it. For which is the output for N1?
Q.
Q is the output for N1. So because of that reason, first we should write the Q. Which is the input for N1? Which all are the input? Two are the input for the N1. So one is S bar and another one is Q bar. Is it clear? So because of that reason, NAND N1 Q comma S bar comma Q bar I have written. So that how that code should be executed. So all NAND gates is have only one output. So because of that reason, first one is output. Next, whatever you have written after one variable, whatever you have written, those all should be inputs. No problem. How it should be executed? Q is equals to S bar NAND with Q bar. It should be executed. We'll get the output in your window. Okay, go for second expression. NAND N2. What is the output? First we should write it. Q bar, comma, R bar, comma, Q. Yes, your code is over. That two are there, your code is over. Next, we should write the end model. We should write the end model. Okay, so this one should be, we have called it as what? Verilog code for SR latch. In this format, we should write it. This one should be, we will call it as structural description, or otherwise we have called it as what? Gate level description. By seeing the gates, we are writing the codes. So because of that reason, we have called it as gate level. Or by seeing the structure of that code, structure of that logical diagram, we are writing the code. So because of that reason, we should call it as structural description. Okay. So any doubts regarding this concept? If there is no doubt, any doubt?
No, no doubt, sir.
No doubt. Okay, so I will give you one assignment. So sorry, one homework. So you can analyze that circuit. So after analyzing the circuit, you should write the gate level description. You should write the structural description. Take it the title of the program. Write a structural description in Verilog. Write a structural description in Verilog of 2 to 4 decoder using NAND gate. Write a structural description. Write a structural description in Verilog of 2 to 4 decoder using NAND gate. Check it here. First, what we should do it here, I will explain the flow. In which flow we should write it. First, we should draw the what? Logical diagram. That logical diagram of 2 to 4 decoder only using NAND gates. First, we should construct that circuit using logical design. Using digital electronics, we should construct 2 to 4 decoder using NAND. By seeing that logical diagram, you should write the code. Can you write it? Can you try it?
Try, sir.
Okay. Okay, you can try it. So I think from 3 to 4 today itself, from 3 to 4, I will explain. I will take a lab today online. In Google Meet, I will take a lab. So within the lab, I will explain first experiment. First experiment of your lab should be a 2 to 4 decoder using NAND gate. Okay, so I will explain that code, and also I will explain the flow of your program. After that procedure, how to execute that code in Xilinx software. Okay, from 3 to 4. Okay, can you try it up to 3 to 4? Can you try it? If you are getting that code and you can post on my WhatsApp, I will check it. Try it. Okay, thank you.